So this last section, we're just going to cover a whole bunch of topics which are related because of nuclear energy, but in a lot of ways these are all separate topics in themselves. We're going to talk about how we detect radiation. We'll talk about half-life of nuclear reactions and how we can use that in dating like artifacts, ancient objects. And we'll also talk a little bit about nuclear energy and the health effects of radiation. So how do we detect a radioactive or radiation, right? And first thing to think about is when you're going to detect radiation, there's a couple of possibilities on what you could detect, but the most common thing that is detected is the particle that comes as part of the decay process. So we have a nucleus. It could go by electron capture, it could go by beta emission, alpha emission. But the most common things we're detecting for are alpha, beta, and gamma rays is what we call them, okay? So when these particles are produced, they're always the sign of a nuclear decay event. So we have a particle comes out, and then we have some kind of counter, and the counter has to be able to detect the particle. Now, typically the way this is done is by taking advantage of the fact that these particles have high energy and can ionize materials as they pass through the material. This is the same reason why radiation can be dangerous for us, because the radiation particles, as they penetrate your tissues, can cause ionization to occur, which can cause the breakage of bonds. Okay. So one of the types of detector is known as the Geiger Muller counter. This is actually an old picture of one, but I like it because it's very clear on how it works. Okay, the way it works is you have a radiation source. So let's just call it a little black box like this, and it's releasing radioactive particles. And so what you do is you take this device called the can, and this can is usually like in a handheld device. So if you've ever watched a Godzilla movie, for example, it's that thing that they hold that clicks, okay? So particles are released by the radioactive source, and they go through a clear window, and inside this can we have argon gas, and the argon gas has a voltage of several thousand volts usually between a wire in the middle and the can on the outside. Now, because the particle is ionizing, what it can do is it can strike an argon atom and cause the argon atom to lose an electron. And as a result, you're going to have electrons and you'll have positively charged argon ions, which then, in response to the voltage, will be creating a current. Okay, so I have this potential energy source here, which is the can, and we can put several thousand volts on it, and then all of a sudden an ionizing bit of radiation comes through and creates ions in the argon gas. The result is electrons will move towards the positive electrodes, and argon atoms will move to the negative electrodes. So this would be equivalent of an anode and a cathode, and pick up the electrons from the can. Well, that causes an electric current to flow. So what's going to be happening is an electric current will be flowing essentially in this direction. Now, in the old school Geiger counters, this was actually hooked up to the counter would have been a speaker, and then or a circuit that was connected to a speaker, and when the electrons suddenly started moving from the ionized radiation, it would create a voltage in the speaker that would cause it to click. So every click that you heard was the detection of a bit of radioactive decay. Okay, so that's a Geiger Muller counter. So anyway, it can detect particles like alpha, beta, and gamma particles that create ionization inside this chamber. It can't, because of the nature of the way the ions are generated, it can't actually distinguish between the different kinds of radiation because they all produce the same kind of signal. Another type of detector is known as a scintillation counter. So the way a scintillation counter works is you take an alpha, beta, or gamma particle again, and it goes into something called a phosphor. And when the particle strikes, depending on the amount of energy the particle has, it can release more or less numbers of photons. So what happens then is the photons then come to what's called a photocathode, which then converts the photons that are received on this end into electrons. So in principle, what happens then is the photocathode is connected to something called a photomultiplier tube. And the way a photomultiplier tube is, it has electron emitting material here. If you remember photoelectric effect, it takes advantage of that kind of effect, where when a particle comes in and strikes this electrode, it causes the release of electrons. Now, what they do in the photomultiplier tube is they have a positive voltage on this end and a negative voltage on this end. And then in between, each one of these electrodes, these are each known as, they're called dinodes, I believe is the correct term for them, but each one of these electrodes is poised at a voltage that is slightly positive from the previous electrode. So this is positive from here, but this electrode here is positive in voltage relative to here. So when the electron strikes this plate, again, photon comes in, produces a number of, ionizing radiation comes in, produces a number of photons. The photons strike the photocathode, which then produces electrons. So the electrons come out with a certain amount of kinetic energy based on the potential, or strike with a certain amount of kinetic energy based on the potential difference between here and here. And the electrons fly out, and they strike the electrode, and that produces more electrons that then are accelerated towards the next plate. So this plate here is a positive voltage relative to here. So if we think of it in terms of pluses, this is a positive here, but this would be doubly positive, and this is triply positive, quadruply positive, that kind of thing. Oh, left a positive out. So they're going to successively higher voltages, right? And every time it strikes the plate, it produces more electrons. This is where the term photomultiplier comes from. A photon comes in, and then that photon is converted into electrons, and those electrons are then multiplied down inside the photomultiplier tube, and this acts as a form of amplification for the signal that comes in the window. So if these are calibrated, whether it's an alpha, beta, or gamma ray can be determined based on the number of electrons that come out in the output end. So the advantage of a scintillation counter is actually it's more sensitive than a Geiger counter, but it can also tell what kind of particles you're dealing with based on the number of photons or photoelectrons that are produced in the process. So these guys again are known as, I think I mentioned this, photoelectrons in here. Okay, so that's how we detect. Another one, and I don't have a picture of this, and normally I just hold one up, since I have a couple of these in my office, but I have what are called dosimeter badges. So dosimeter. So I just realized I could just go on the internet and show you pictures. Here's examples of some dosimeters. These are known as Dosimeter Pens. These are not as common. I usually hold one of these up in class because I actually have one. Mine looks like this one. It's a little antique looking thing. But these are essentially reusable, and what you do is you look down the inside of the dosimeter pen, and it gives you an idea of how much radiation you've been exposed to. Many of these are like resettable, so you can reset them and be used over and over and over again. Now, there's also dosimeter badges. Like these. These are the ones you see in hospitals. You wear it clipped onto your body. You usually pick it up when you come to work. You clip it onto your body. When you leave, you drop it off. And what the dosimeter badge does is the old ones had a piece of film in them. I'm not sure if the new ones are digital yet, but the old ones had a piece of film in it, and they could detect how much radiation you were exposed to based on the exposure of the film. So the bad part about dosimeters, though, is you have to be in the radiation in order to detect the radiation on the badge. So it's basically to tell you if you should go back and get treated. It's unfortunately not going to tell you ahead of time whether or not you're going into a dangerous situation. That's what Geiger counters and things like that are for. Anyway, so those are examples of dosimeters, and those are another way that we commonly measure radiation in the laboratory. One other story I always tell is a guy that I worked with. He worked in Kiev at the university, and I used to work with him when I was in industry. And he had come over from Kiev, and he would always tell the story of when he left. And he worked in a lab that had a radiation, very sensitive scintillation type counter. And they were in the lab one day, and suddenly the radiation spiked through the roof. And so what they knew had happened, because I guess they were not far from Chernobyl, they knew that the reactor had melted down. And so as soon as he saw that, he says, he shut the windows and the doors to the lab and left. And I think that's actually when he left the Soviet Union. So this was quite a while ago during the meltdown at Chernobyl. But yeah, so he had advanced warning when it happened that he should be getting out of town right away. So we know how to detect nuclear decay events. How do we quantify it? And the way we do it is by measuring the rate of decay, or the number of nuclei that are decaying per second. So rate is nuclei per second, but it could also be done in units of Curie. So Madame Curie, like Marie Curie, right, who did so much of the pioneering research in radiation, has had a unit named after it. So if you detect 3.7 times 10 to the 10th nuclei per second, now think of how fast that is, right? That's, if you just had 1 times 10 to the 10th nuclei per second, you would be seeing 10 decays, right, per nanosecond, like 10 to the minus 9 seconds, right? So this is an extremely fast count, okay? And when we're thinking about nuclear decay, you have to think in those kinds of numbers, because it doesn't take much, right? Considering what a mole is, it doesn't take much of a mole to produce 10 to the 10th. So anyways, the unit is Curie, and it's 3.7 times 10 to the 10th nuclei per second. Now, let's start thinking about what this means, right? I have a rate. And in reality, a rate is a change in the number of nuclei per second. And I put it like this is like units. But it's the change in the number of nuclei over the change in time. And it turns out that will be equal to a rate constant times the number of nuclei, like this. And n is the number of nuclei that you start with. Now, if this looks vaguely familiar to you, it should. It's because rate, right, which is delta A over delta T, is equal to K times the concentration, like that. So this is a first nuclear decay is a first order process. So that's why we end up with delta N over, delta T, kind of tired. Delta T, right, is equal to K times N. Well, there's other equations that we associate with this, but one of the things I wanted to sort of remind you of is what a first order decay looks like, and then we'll put some of the equations on this graph. So this is a first order decay curve. This is for carbon-14, and carbon-14 has a half-life of 5,730 years. Now, if you remember what that means, then is after one half-life, half of the material has decayed away or has reacted, like in a kinetic experiment. Half of the reactant has reacted and produced product, right? And you're only left with half remaining. Now, in a first order process, the half-life is always the same. So that means after another 5,730 years, which comes out to be 11,460 down here, then you have half of the half that you had, and if you go to 3 half-lives, then you have a half of a half of a half, or an eighth of what you started with, and then a 16th, etc. All right, now, the equations that we use to generate this line, the equations I use to generate this line, are the half-life equations. So in chemical kinetics, well, let me do it here. In chemical kinetics, we know that the rate is equal to is K times C, but then we know that the concentration of, ln of A, T over A0 is equal to minus KT. That's one of the things that you can derive from this equation. There are other forms of the equation as well. You can also write you can take the antilog of this equation and end up with AT over A0 is equal to e to the minus KT, like that. So then AT, this is one of the handy equations, is equal to E, or A0, e to the minus KT, like that. Well, really all we've done in writing the equation like this or like this is change the symbols. So you can say something, for example, like the natural log of NT over N0 is equal to e to the minus KT. Or you can say NT is equal to N0 e to the minus K. Oops, I wrote that as a subscript T. Like that. And again, this is the form of the equation that we're using, but it is essentially the same as this equation here. So that's what actually gives us this half-life curve. I just took and put it in Excel, and I did the time in years. I plugged in the half-life. I derived the rate constant from the half-life and plugged it in here. So one of the other things that we get out of half-life analysis is that T1 half, or let me do it like this, K is equal to the natural log of 2, and I always forget that what that is, divided by T1 half. So what I did in doing this graph is I knew the half-life was 5,730 years. I calculated the rate constant, and then I ended up plugging it into this equation to calculate the nuclei left at different times. So when you are treated with a radioactive isotope, it will reside in your body for a period of time. And for example, people who have overactive thyroid, one of the treatments is to give them a radioactive isotope of iodine. And as a result, what happens is the iodine gets taken up into your thyroid. And they calculate the dose out that's needed to shrink the thyroid, basically kill part of the thyroid, so you don't produce as many of the hormones that are produced in your thyroid. It happened actually to me when I had a friend who had a hyperactive thyroid, and they went ahead and did the radioactive treatment of him, and he came to the lab and he was super excited because he knew we had a Geiger counter and he wanted to show me that he was radioactive. So sure enough, we grabbed the Geiger counter and he was clicking away, and then he went home because you're not supposed to be out in public when you do that. But when you're a scientist, sometimes you do these stupid things. Anyways, so let's do a calculation. We're going to calculate the percentage, and we'll do the mass too, I guess, of a 0.1 gram sample of technetium-99 that remains after 28 days. So we know the decay is first order, right? And we can either estimate this or we can calculate it specifically depending on what our needs are, right? So, for example, the half-life of technetium-99 is 6.09 days. That means after 6 days, right, you have half, and then you have after 12 days, and then 18 days, and then after 24 days, what you'll end up with, 24 days would be 4 half-lives, so a half and a half and a half and a half. So you're down to 1/4. Sorry, let's do it like this. How to do the estimate, right? It's going to be, initially you have a half of the initial amount, so I take 0.10 grams, and after the first half-life I have half, after the second half-life I have another half, right? A third half-life I have another half, and a fourth half-life I have yet another half. Now, if you think about what this reflects, this is 6 days later, this is 12 days later, this is 18, because every half-life is 6 days, right? And then we're at 24. So 28 days would be 2/3 of the way, right, to the next. So this would actually represent 5 half-lives. This is between 4 and 5 half-lives. So you could estimate it doing that, right? And you'll get pretty close to the answer. Or you could use the equation like this one. So there's a couple of things to recognize. We have the half-life as 6.09 days, and we need to calculate a rate constant if we're going to use the calculation equation. So that's going to be natural log of 2 divided by 6.09 days. And I'm just going to leave it like this, okay? And then what I'm going to do is I'm going to say NT over N0 is equal to e to the minus kt, and what I'll be putting into this is I'll put in e, then I'll have natural log of 2 over 6.09 days times 28 days. So if I do that calculation, I'm going to get 0.0413 for NT over N0. This translates into 4.13%. Okay? So after 28 days, I should have 4.13% left. Now, if I wanted to know, and I did put this little note here, right? This is the fraction, so to get percent, I just multiplied by 100. On the other hand, if I was ballparking it, right? If I did T 4 half-lives, all right, then I can do, I would find that I could go 0.10 grams, and then I can do it times 1/2 to the 4th, or I could do 0.10 grams, and I can do it to 1/2 to the 5th, right? This represents between 4 and 5 half-lives. That would be between 24 and 30 days, which this is. When you do the calculation based on this value, right, and these half-lives, you get numbers like 6.25% remaining and 3.25% remaining. And so what you find is between 4 and 5 half-lives, this number sits right in the middle of those two numbers. So it depends. Like I said, it depends on how accurately you need to know the number. If you only care within the half-life, then this is sufficient. If you need to be more exact, you'll do something like this. Now, if you wanted to know the grams, right, all you need to do is take 4.13% of 0.1 grams, and that tells you how many grams of material you have remaining. So if you remember, we talked about transmutation reactions a little bit with Rutherford, and when Rutherford was studying transmutation reactions, one of the things that they talked about is, of course, one type of element changing into another type of element. There was a scientist named Boltwood in the United States, a chemist actually, and he was pretty fascinated by the idea of being able to tell when a radioactive event took place. And he thought to himself, he sort of made this connection. He says, well, if I could count the rate at which nuclei are decaying, I can relate the ages of different elements that he's finding. He's called in a radioactive decay series between like uranium and lead, and sort of tell how long each step in the process took place. And so Boltwood came up with this idea of being able to age an item based on its radioactivity levels. Okay, so its premise is pretty simple. Okay, the premise is pretty simple. We have carbon-14 in our bodies, and at some point, and we get the carbon-14 just by naturally eating. At some point when we die, we'll call that 100% of our carbon-14 in our body. So we sort of reach equilibrium with the carbon-14 that's in the atmosphere. Well, once we die, we stop eating, in essence, and we begin to decompose. But more importantly, for the idea of radioactive dating, right, is that the carbon in our body also decays by a process of nuclear decay. And if we can measure the amount of carbon-14 based on a decay curve, or the math behind the decay curve, what we can do is we can estimate how old an object is if we just know how much carbon-14 it had in its body at some point. Now, oh yeah, so this is my graph. This is you before you die. You're eating carbon-12 and carbon-14, right? And this is always in a fairly constant ratio. Now, this is organism dependent, and so but for us is basically we're eating the ratio carbon-14 to carbon-12 that's in the atmosphere. Some plants actually preferentially will, I believe, extract the carbon-12, but I don't remember exactly how it works. But there's some plants that have this ability to discriminate between the carbons. But anyways, at some point you die and you stop eating, and so basically the carbon-12 is a stable isotope and the carbon-14 is an unstable isotope. And what happens is over time the ratio of carbon-14 to carbon-12 decreases. And it's that ratio that we measure actually to tell how old an object is. Okay, so real quickly, where does this carbon-14 come from, right? It turns out the carbon-14 comes from the upper atmosphere. So what happens is neutrons come in from space, and in the upper atmosphere, they react with the nitrogen-14 to produce carbon-14. Now, you could do the math here. I'll let you figure out what this particle is. But the carbon-14 then trickles down from the upper atmosphere, and then we sort of eat it as a part of our diet. Now, one of the assumptions is, there's two assumptions, or two ways to look at the assumption. One assumption is that the carbon-14 has been coming from outer space at a fairly constant rate. But even if it hasn't, we can actually go back and calculate the amount of carbon-14 that's been falling on the Earth for approximately the last maybe 50 to 100,000 years. The reason it gets hard to go past that is because the rate of which carbon-14 decays is fast enough that by the time you get to, let's say, 50,000 years, it's really hard to detect the carbon-14 reliably in a sample. So the problem we're going to be working on here is on the right, and some background information and a problem strategy are here given on the left. So what we're going to do first is we're going to estimate how old the bone fragment is. It says a bone fragment yields 2.3 events per second. And the number of events per second is directly related to the amount of carbon-14 left in the sample, right, per gram of carbon. How old is this bone fragment? Modern carbon yields 15.3 counts per second. So the way we're going to estimate it is this. All you have to do is say, well, 15.3, if I multiply that by a half, and by a half again, so 1/4 of that, right? So 15.3 divided by 2 divided by 2, that gives me 3.825. This is how many counts per second you would expect if it was 2 half-lives. This would be 2 half-lives. If you do another half-life, this is 3 half-lives, right? Then you get 1.9. So like that. So this is 3 half-lives. So I know, it's just right off the bat, you notice how 3.825 is above 2.3 and 1.9125 is below the 2.13. I know that this is between 2 and 3 half-lives old. So what's 2 half-lives? 2 half-lives would be 5,730 times 2, and then 3 half-lives would be 5,730 times 3, right? It is actually reasonably close to this value and a little bit further from this one. So I'm saying it's closer to the older number, about the 15,000 or so years old, just based on the number of half-lives. Now, one of the reasons why you would do something like this is sometimes that's an acceptable age range. On the other hand, it's also a good way so that when you do the calculation, you know you're in the right ballpark for the answer. Just estimate the number of half-lives and see about how big your answer should be. Now, the way we're going to do this calculation is we're going to use essentially first-order kinetics, but we'll use this form of the equation because it's a little bit easier to work with. Natural log of nt over n0 is equal to minus kt. And we're really going to be looking for t, and that's going to be equal to negative ln nt over n0 divided by k, by k. Well, we could calculate k. That's going to be the natural log of 2 divided by 5,730 years. And then nt, right, is 2.3 counts. That's the current number of counts. And n0 is 15.3, so that would be this value here. So you go ahead and you do that calculation, and what you get is the object's about 15,000 years old. And again, the reason for doing this calculation initially is just to bracket the answer to get a good idea what it should be, so you'll know approximately what it is. I should say that there are some limitations to carbon-14 dating. I mentioned one already. Up to about 50,000 years, it's not too bad, but beyond that, it gets pretty dicey because the actual amount of carbon-14 that's left that's actually decaying is really small. The other limitation is you have to assume that nothing has happened to alter the carbon-14 content in the sample. So as a control for that, what scientists do is to go back maybe 15 to 20,000 years, what they do is they look at core samples from trees and lumber samples from trees. So for example, if you take a tree, I think the oldest living trees now are somewhere between 3,000 and 5,000 years old, depending on the kind of tree we're talking about. And actually, a bunch of them are in California, the redwoods, and there's another bristlecone pine, I believe. Those are the oldest trees on the planet. But we can go further back than that by looking at lumber samples. And so what we do is this. We basically, the way a tree grows, it starts in the middle and it adds layers, right? And all the growth is on the outside. So effectively what gets done is the carbon content of each of the rings is examined, and you can go back then and historically correct the carbon-14 rate of production based on the carbon-14 content of those tree rings. Then what happens is when you run out of like live trees, or you don't want to sample the live trees because you know it's a 5,000-year-old tree, then what you could do is you can look at lumber samples and then match up tree rings, because the width of the ring is very much dependent on the growing conditions, and so they act like fingerprints for time. And so what you do then is you take old wood samples from artifacts and you look at the tree rings and you can line those up. The other way that they do carbon content is they go to these sort of undisturbed I don't want to call them lakes, but I guess they are lakes in the highest northern regions of our planet. And what they do is they look at the sedimentation in those. So they have a very brief growing period. And what happens is algae blooms and consumes the carbon from the air. That falls to the bottom and creates a sediment layer. And apparently you can core the sediment layers and get back many, many tens of thousands a year beyond what you can a tree. And we can also look at carbon content in ice core samples and stuff, like the samples that are being held in Sweden, for example. Anyways, there's a lot of ways that we can correct this back many years, but the bottom line is if you really go past about like 50,000 years, it's really not a use. Carbon-14 is not a very useful technique. On the other hand, you can also do what's called Thermo Chronology. And Thermo Chronology, what they do is they look at isotopes that were trapped in molten rock samples, basically, and then look, for example, at uranium and ratios of isotopes produced by uranium for uranium-235 and uranium-238. So there's a decay series between uranium and lead that produces a number of different isotopes. And based on the half-lives, you can estimate how old those rocks are. And the half-lives we're talking about now are in the 700 million years to the 4.5 giga years, so 10 to the 9th years. So the half-lives being much longer means the samples decay at a slower rate. While they don't give us much precision about the exact dates, you can measure dates in a much larger time span, with the relative precision being about the same. Okay. So one of, again, the many topics in this last section is transmutation reactions. And in a transmutation reaction, you have a target, which is an element, and a particle that comes in and strikes the target, and then that produces a daughter ion and oftentimes other particles that come out of the reaction. There is a shorthand for these transmutation reaction. This is the target that's being struck. This is the particle that's coming in. This is the isotope that's produced, and this is the sort of the particle that's coming out. Now, in order to do this, though, you really have to be able to push the two atoms together with a lot of force. And the reason is because you have to get, there's an like a large positive charge here. It's very hard to get a particle into that field. So in order to do that, you have to take particles and make them move really, really fast, right? So we use something called an accelerator to do that. Now, one of the original accelerators looks like this, okay? And this is the kind of accelerator that you would have found in Cambridge back in the early 1900s, I believe. They have samples of these. They actually have another little museum, and you can see these little samples of the Ds that are in the museum. And in Oxford, actually, I've seen these at Oxford as well. But what a D is a metal disc, right, that's hollow on the inside. And what they do is they take and change the voltage back and forth between the two Ds. So these are Ds because they look like Ds when you stand them on end. And then what happens to the voltage is, let me give you an example. Here's a plate, right? Two plates, two metal plates. Let's put a charge in the middle. And then let's make this the voltage. The voltage is going like this, okay? And this is positive, and this is negative. So what's going to happen is the voltage is going to be more positive, and then it's going to swing to negative, and then swing to positive, and swing to negative. So this voltage is going to be going up and down. And what happens to this particle? Well, when it's positive, this particle, if it has a negative charge, for example, it's an electron, it'll move towards the positive plate. On the other hand, if it experiences a force that's where this is negative on this side, so we're at this part of the cycle, then what ends up happening is the particle will move down this way. Okay, so what you can do with this particle is you can make it oscillate back and forth between the two plates by oscillating the voltage back and forth. And the behavior for positive particles and negative particles will be exactly the same. It's just they'll go in opposite directions of the voltage relative to the applied voltage. So in essence, that's what they do in an accelerator, but then they have one other trick that they do. And the trick is they put a magnetic field going up perpendicular to the plates. Okay. So what that causes to happen is it causes the particles to experience outwardly, like an outward force. And so as the particle is accelerated back and forth, instead of just going back and forth, it begins to cycle out and go wider and wider and wider, until eventually, when it's going fast enough, it leaves the D, okay, and can be used to strike a target. So in our notation that we showed over here, right, this would be the nitrogen gas on the target, or nitrogen, the element nitrogen in a sample. And this would be the alpha particle that's being accelerated. So when this plate is positive, the alpha particle actually wants to move in the opposite direction. And then when this plate is positive, it moves towards this one, right? All right, so now just to give you a perspective, if you stand these Ds on their side, they're about 5 feet long on a side. Okay, so they're pretty big. So this makes it look like it could be relatively small, but the ones I've seen are actually fairly large. Doing this, you can get about a mega electron volt on a particle. Okay, 1 mega electron volt in terms of energy on the particle. When it leaves here, it has 1 mega electron volt of energy. Now, if you want to go to higher energies, and the reason you'd want to go to higher energies is you want to explore like the structure of the subatomic particles that we know, the protons and neutrons. Then what you have to do is you have to use a larger accelerator, and this is one that many people in California have driven over. This is Highway 280 on the coast, and this is near Palo Alto, California, near Stanford. This is the Stanford Linear Accelerator, or the SLAC. Okay, and these are buildings, and this is a freeway, and these dots are cars. Right? So in the SLAC, what they do is they start the particles in the linear accelerator. They start pulling the particles and accelerating them towards this complex down here, which is the complex used to sort of receive the particles. They get filtered out and sent to different research facilities. I had a student who worked in this facility for many years, actually went straight from Fresno City College, did a summer internship, and then sort of found himself stuck over here. He couldn't stop working. He's enjoyed it so much. But anyways, this is the Stanford Linear Accelerator, and this will get you from mega electron volts, right, to giga electron volts. So that's 1,000 times more energy than this accelerator. And then if you want to go even bigger, then you have to go to this one. And this is actually Fermi National Laboratory. And this laboratory is just out of Chicago. And I thought, oh, it'd be fun. Here's Google Earth, right? And if you zoom out, this is the address for Fermi Lab. You can see the accelerators here. And you can keep zooming out. And this is Chicago that's over here. This is where my nephew is studying. All right. And so you can't see it. You know, it's not like it's so big you can see it from outer space. But this is Lake Michigan that's over here. So that's sort of what it's next to. Anyways, it's a huge facility. Anything that you can find reasonably easy on Google Earth, just by looking, has got to be pretty large, right? So anyways, it's right in here, Yeah, oh, there it is. Right there it is, that guy right there. Okay, anyways, that's what this picture is here. This is a sort of an aerial shot of Fermi Lab. This gets up to the tera electron volt. It used to be the largest one in the United States. It was 3.9 miles in circumference. So if that tells you how big those are. Going around, and what they would do is, again, get the particles accelerating through this facility, and then the target where they actually do the research is down here, and there's probably some labs along the side here. The only one that's bigger now is the Large Hadron Collider, and it's still in the tera electron volt range, but um, yeah, it's on the higher end. Anyways, that one is 16.8 miles and uses like superconducting magnets to accelerate particles. The way they actually, in a linear accelerator, just to explain how it works, it really works kind of like a dog race. I don't know if you've ever seen a dog race, but they have an electronic rabbit, and the electronic rabbit is always in front of the dogs, and it's designed to stay in front of the dogs a certain distance. And the dogs are trained to chase the rabbit. So what they do is they start with particles that are down here. Let's say they're positive particles. They make a negative charge appear in front of it, and that negative charge is timed to appear at different points along the linear accelerator. So what ends up happening is the particles just keep going towards the positive charge, but the positive charge keeps getting ahead of them. Anyways, that's kind of the idea. And again, this is a tremendous amount of energy. Like, this is small city type of energy. It's the energy required by a small city and all its residents. So these are the accelerators that are like the top accelerators that are being used now, like SLAC and Fermi, and now the LHC, the Large Hadron Collider in Switzerland. So this is one of those areas I know very little about, radiation exposure. So I'll tell you what I know. There's really not much expectation in this area, really. But radiation is measured in something called Rads, and Rads is the amount of energy it takes to deposit 10 to the minus 2 joules, or a centijoule, right, per kilogram of tissue. And then a gray is another unit, which makes more sense. It's joules per kilogram. That's one way we measure radiation dosages. The other way, which is probably more practical, is called the REM, the Roentgen equivalent in man. And it has this weird, it's related to this weird unit called the sievert, right? 0.01 sievert. Is REM, an REM. And what they do when they're doing REMs is they're trying to take into account both the ionizing power of the radiation and its ability to sort of induce undesirable ionization in your body. Okay. So 1 sievert is equivalent of a 5.5% chance of cancer, roughly, right? And if you have 100, 1 sievert is also about 100 REMs, right? And this is enough to induce radiation sickness. That is, what happens is your body is exposed to enough radiation, it's caused enough damage that you become sick from it. And one of the things about radiation doses, from my understanding, is these are cumulative doses. So when you get exposed to radiation, it causes damage in your tissue, some of which gets repaired, but you accumulate the damage over time. Now, the different kinds of radiation decay particles have different effects, and so I found a sort of a cheesy diagram here for you to reference to. But there are alpha particles, and alpha particles are not dangerous unless they get into your body. The reason is even though they are some of the most energetic particles, they can't get through your tissue because they're so large. Okay, so they basically bounce off your skin. Where they're dangerous is when you ingest them or you inhale them and they get into your soft tissue, because your soft tissue doesn't have the dead layer of skin on top, the epithelial layer. Beta particles are not necessarily stopped by the epithelial layer, but they can be stopped for the most part by a layer of clothing and your skin, right? So it might go a few millimeters into something, but it's not going to go that far. And then there's gamma rays and X-rays. Now, gamma rays and X-rays have the highest potential to do damage because they're photons and they can pass right through matter, and they also have a lot of energy, so they're able to ionize like DNA and protein molecules. And so this is what makes them more dangerous. The last thing we'll talk about is nuclear reactions that lead to the production of nuclear energy and bombs. Okay, so it's all based on E is equal to mc squared. And I'll point out to you that when you have a nuclear reaction, the ones that we're most familiar with, which are called fission reactions, what you're doing is you're usually inducing a type of chain reaction. That is, if you have a sample of uranium-235, right, and you induce it to decay, and this can be done by simply shooting a neutron into the nucleus. Now, I say shoot, it actually is a relatively low energy neutron, but because the neutron doesn't have any charge, it actually can penetrate into the nucleus fairly easily. And then what happens is that causes the nucleus to be unstable. And then when it decays, it can produce elements like barium and krypton, but it also produces excess neutrons. And these neutrons can go and find another uranium atom, okay? And then that can induce decay, and you don't always get the same products out. So in this case, there's a rubidium and a cesium, a strontium and a xenon, and a bunch of neutrons. But because you're always producing excess neutron, there exists this potential for a chain reaction, and at each reaction you're producing energy. Now I'm going to tell you a little story. I'm going to go back to this picture here, I think. And this was during the Manhattan Project. And in the Manhattan Project, what they found is if you took two masses of uranium-235, and they put them, the way they did it, and you put them together, okay, what you would notice happening is you would notice there would start to be a glow of radiation in between the two particles, or pieces of uranium. And the way they did this experiment is they created like a little train, basically, and they put samples of uranium on these little carts, and this had uranium in it, uranium-235, and they put another one, and it's on a little track, separating each other like this, right? And then they would move them towards each other. And as they got closer together, what they would see happen in between, right, is they would start seeing sort of the glowing of radiation between the two pieces of uranium. What was going on, right? Well, when they brought these two things together, what was going on is one object was producing excess neutrons that escaped it, right? And they were being captured by the other one, and then it would start to release more neutrons. So basically, these are like neutron guns. They're shooting neutrons towards each other, and that's causing the air in the middle to ionize. And this led to the idea of something called a critical mass. See, not all chunks of uranium explode, and the reason chunks of uranium don't explode has to do with how much uranium there is. So let's say I have a chunk of uranium that's that big, and an atom over here produces neutrons that are flying out in all directions, right? Well, it's pretty clear that some, and remember, matter is mostly empty space, right? So what happens is some can leave the object, some will travel through and potentially hit another uranium atom, but since matter is mostly empty space, a lot of these can escape the uranium without ever striking anything. On the other hand, when that gets big enough, right, maybe make it a little bit bigger like that, and then you have that same one, well, still some can escape. But the longer these travel through the uranium, the better the chance they have of striking another one and re-releasing neutrons in all directions. Okay. So this is this mass at which this becomes a self-sustaining nuclear reaction. that mass is known as the critical mass. Now, the sort of tragic end to this story is they didn't know a lot about this at the time they were doing the Manhattan Project. They were wheeling these two things together, and what ended up happening is one of the positions got stuck. And so these two subcritical masses is what they had at the ends of these little like train cars, right? These were not giant. These were like people-sized things. They got stuck and began to emit a lot of radiation. And so what ended up happening is the scientist who was running the experiment realized like the danger that everybody was in because he was afraid that it was going to explode because their goal was to make a bomb. And what they were testing was the idea of forcing together subcritical masses to start a nuclear reaction. He went in there and separated it with his hands, and within a few weeks he was dead from radiation poisoning. But it was super intense radiation that's being released when these two are close together. Simply because you're spontaneously creating, right, self-sustaining, creating these nuclear reactions. So this is what's going on when we do a nuclear bomb. And the way they eventually made like the bombs that fell over Hiroshima is they used two subcritical masses of uranium. And then they had a conventional chemical explosive. And when this explosive went off, what it did was shove this piece into this piece. See a little wedge there, right? And that became a mass of uranium that was above the critical mass. And then you had this self-sustaining, uncontrollable nuclear reaction that we know of as a uranium nuclear bomb. They were pretty crazy about these kinds of things. They were trying to figure out all kinds of ways that it could be weaponized in the early 40s and 50s. So this is actually a movie, and I don't think it runs anymore. Yeah, it's actually a movie of a uranium nuclear depth charge. And what they were doing is firing basically a depth charge into the ocean, and this was the result of the depth charge. And if you look at these little things on the side, these little sticky things, these are actually warships, so like battleships and aircraft carriers that were being scuttled. They were basically used as the test for this nuclear depth charge. So basically they created this huge shock wave, right? And I'm assuming they killed everything in that region, but it's crazy what they were doing. So we have more subtle ways of using it now. And so this gets us into the nuclear reactor business, okay? So in a nuclear reactor, what they do is they use uranium that's been embedded in ceramic fuel rods. So the uranium that's used in the fuel rods is typically uranium-235, the same stuff made as the bomb that makes the bomb, but it's not in that sort of pure form that can be basically exploded. And the other thing is in the fuel rods, what they have is this ceramic which holds it together, but they have the uranium in the fuel rods all separated from each other. So in order to keep the nuclear reaction under control, what they have is something called control rods. So you take a control rod, and the control rod has neutron-dense isotopes in it, sort of like boron. Boron is actually very good at absorbing neutrons. And so you can imagine what these act as like dampers. So where this one wants to cause a nuclear reaction and this one and vice versa, if you drop a control rod in between the two fuel rods, what that does is absorbs enough neutrons that it stops the reaction. So when the reactor starts, before it's turned on, all these control rods are essentially in the bottom position, and they're keeping the neutrons from going back and forth between the fuel rods. Then to start the reaction, all you have to do is lift the control rods out from between the fuel rods. Once the nuclear reaction starts, what they do is they use high pressure water, basically, and a pump, basically to superheat water and then pump that through. And that heat that's from this superheated water is used to generate steam in another body of water. Okay, so I'll talk about that in a second. This cool water then is returned back to the reactor, right, to be reheated again, and then it comes back through, and then it goes through, is cooled by the creation of the heating of the water in the secondary container. So one of the things to keep track of in the reactor is that this pathway, right, is isolated from everything else. That is, it's just, if the only way that this water gets contaminated is if this breaks, right? But now this water is heated and it's used to generate steam, and then the steam is used to drive a turbine, and the turbine is basically an electric generator. So now we have a second system of water, right, that comes this way, and then that's cooled on this side by water from a third source of water, but again it's isolated like that. So in the dome of the nuclear reactor you have these two, and if you've ever seen a nuclear reactor, let me pull a picture up. This is the Diablo Canyon nuclear reactor in California. So this is the actual nuclear reactor that's here, okay? That's this dome here. So we have a nuclear reactor that's generating this is heavily radioactive water that's in here. This is always contained within this unit, or only removed when necessary, right? And then this is water that again is isolated from the outside environment still. So if you were to get radiation in here, the only way you could get that is one of these broke, right? The only way you could get radiation outside is if both of these systems broke, and presumably by the time one of them breaks, you've already stopped the reactor, and this doesn't happen. So steam gets generated in this system, right? And then they use cold water from a lake, or in the case of the Diablo, right, they're actually using the ocean to cool the secondary water in the nuclear reactor. So this is enough, though, to generate a huge excess of energy. So it has enough energy not only to run all the pumps, but it also has enough then to provide power to the grid in California. Although I'm trying to think if they're commissioned to shut it down soon, I think, if they haven't already done it. Anyways, one other thing I wanted to point out about this particular design is that if there's ever power loss to the reactor, like something happens, these control rods are being held up by, not by default, but by the actions of like motors and stuff. And as soon as the power goes off, these control rods drop down and stop the nuclear reaction. So they're actually fairly well, like they thought it out fairly well to keep people safe. Although there have been accidents at nuclear reactors, I will freely admit, of course, but these are designed actually to try to minimize any real serious accidents. And oddly enough, I think if there's ever really a problem, that these domes can be filled with concrete, sort of like to lock all that junk in place, although I don't know if that's the best design, but it seems to be the way it's done. All right, the next thing to talk about is fusion reactions. So this was fission. We're going from, big atoms to smaller atoms. So this is fission, F-I-S-S. And then fusion reactions are when we go from lighter elements to heavier elements. So this is the same process that takes place in the sun. The temperature that it takes place at is 100 million degrees Celsius, and it generates what's called the plasma state. And in the plasma state, you've completely separated all the atoms from their electrons. Okay. The natural occurring source of this kind of energy, of course, is stars. But on Earth, we're trying to do it with both what's called inertial and magnetic confinements. The big payout for this kind of stuff is that, if you have 1 gram of deuterium and tritium mixture, it's the same amount of energy in 2,400 gallons of oil. So it produces a lot of energy. And what comes out of it? At the other end, there's not a lot of hazardous waste that's produced. It's helium and neutrons, right? So you could actually sell balloons on the output, I guess. Anyways, well, probably won't. It's also, you could think of it as if you had 9,000 tons of coal, that's the same as about 5 pounds of reactant material over here. So anyways, yeah, there's a huge payout if we can figure out how to use this, right, to produce energy. We won't be producing any of the greenhouse gases and any of the sort of wasted heat energy, and all of it would be captured as like useful energy and very little waste being produced. Um, the way that we're going to do this is in what's called a Tokamak Reactor. I'll show you a picture of it here in a second. This was the original timeline, but it's kind of funny because you notice this should be done by now, right? So the new timeline is this one. They basically, construction of the Tokamak building, right? Um, that was all supposed to be right in here. This is 2011. I don't know what happened, but they got pushed way back, and they extended the number of years. They're hoping to light the first plasma in about 4 or 5 years. We'll see if they actually get to that. But this is a more recent timeline. So this is a Wikimedia page, a picture for the inside of the Tokamak reactor, and what actually they do to make this reactor work, or they're going to try to use to make it work. And you can see the scale of it because it has a person in it. They create this large magnetic field, and it turns out the plasma, because you think about, you're trying to do this nuclear reaction, it's going to produce temperatures of 100 million degrees. You can't stick it in anything that's physical because it'll melt it, right? So what they use is they take advantage of the idea that all the particles in the plasma are charged, like this, and they create a magnetic field to contain it. And so there'll be circulating magnetic field inside this Tokamak reactor, and hopefully they'll be able to sustain the fusion reaction in that magnetic field, and then somehow extract that heat energy and produce power from it. But anyways, it's a big multinational effort to produce this first Tokamak reactor, and people are also working on smaller versions as well. So, the way technology works, processors get smaller and faster. They're trying to do the same kind of thing, even as they haven't built the first one, trying to build smaller and better reactors designs. So anyways, that basically covers it for this chapter. And if you have questions, of course, you can always text me or send me an email.